name is Ben-Yaakov. I'm from Ben-Gurion University, and the objective of this presentation is to look at piezoelectric devices and associated electronics, but from the power electronics point of view. In other words, I'm not going into all the details of the physics and the materials, etc. In fact, I don't know much about it. We are working the power electronics part of it, that is driving elements, understanding how they behave from the electrical point of view, and then rectifying if it is a transformer, etc. Now, I've organized this seminar such that people who don't have experience will have a feeling of what are the different piezoelectric elements, and those who do have experience in the area, I hope they'll find some new things that they can learn or see what we've been doing. The outline, let me go over briefly, is we have the first part, an overview of the devices that I'll be talking about, just to have a feeling of what are the devices which are available today. We're talking about actuators, vibrating vans, motors, generators and dampers. We'll talk about transformers and then some other odd devices. By the way, if there is any question that you like to ask, don't wait, just go ahead and ask. Let's not be too formal. We are a very small group here. So if there's something which is unclear or needs maybe explanation, please let me know and we'll go into it. Now, the second part will be the issue of modeling of piezoelectric devices. Again, I'll go over the devices that I've talked about in the first part. What are the models that electrical models that can describe them, motors, generators, transformers, and then we'll go a little bit about the issue of parameter extraction. That is, how do we extract the parameters of the model and get some into issues of nonlinearities and some other problems. Then we'll continue with the issue of drivers, and again we'll cover the various elements, actuators, vibrating van, motors, and transformers. And then when it's appropriate, of course, when we're talking about transformers or generators, we have the rectification part. So we'll talk about the inductive and capacitive filters, and then I'll present a resonant rectifier that we've been working on, which can be useful in the case of a generator, and since it can obtain or get some more power out of the device. Finally, I'll talk about an issue which is a little bit open as yet, and that is piezoelectric transformers which are driving cold cathode fluorescent lamps. Now, there are some problems of stabilities, dynamic stability, and we did some work on that recently, so I'll present some of the results that we have. We'll talk about issues of concept of incremental impedance, which is important when looking at the dynamics, and then I'll introduce to those who are not familiar with the technique of envelope simulation, which could be extremely useful to handle problems like this. Now, I've included in the material that I've submitted two appendices. One is talking about, these are also slides, talking about envelope simulation, the concept and how you implement it. And then the second appendix is talking about resonant rectifier, which I'll go briefly during the seminar, but we may not have time to go in detail. Now, if we'll be doing our job well and there'll be sufficient time, I may be able to go over the appendices myself. If not, this is just a if not, you're welcome to, of course, look at them. They're sort of detailing the two issues, which need some more, details in order to understand. We'll cover them in the seminar, but not in a very large detail. Okay. Now, let me start then with the introduction. Piezoelectricity was discovered about 100 years ago by the brothers of Pierre and Jacques Curie. And at the early ages, it was used mainly for sonar, microphones and pickups, and of course the quartz resonator are piezoelectric material, and they are part of this family. Now, since the introduction of ceramic piezoelectric material, then we've seen development of more powerful sonars. Of course, there are igniters. There was a period in which a lot of tone transducers were used for communication. Now it's more digital. And then the ceramic resonator were used. Of course, today we're using buzzword speakers. And we have now a growing family of piezoelectric motors that I'll talk about, and of course actuators. And then finally we have the piezoelectric transformers, which are now emerging as a devices for power electronics, or power conversion, I should say. And then there are some more, let's say, exotic devices that are now also developing, like dampers, power sources, and others, which I'll talk a little bit about. Now, the main emphasis of our seminar will be piezoelectric transformers, but as I've said, I'll try to cover other elements as well, just to give the broad view of this technology. Now, starting with the very simple-minded effect of the piezoelectric phenomena. We have a piezoelectric material, and if we have two electrodes deposited on it, then due to the fact that there is a mechanical to electrical interaction, mechanical is stress and electrical is electric field, then of course we'll have a other expansion, or we'll have a compression of the material. The very simple phenomena, this simple phenomena is used in the actuator. The actuators are basically a stack of rings made of piezoelectric material, and the reason it's not one piece is because we like to build a fairly high electric field inside, and therefore obviously if it'll be one piece, then there'll be a huge voltage that you need, and in this case, by breaking them into disks, then of course you get a higher electric field per voltage that is applied. So these are plated disks, and by applying a voltage between the electrodes, it'll expand, and these are used for positioning, small deflection. We get around the micrometer range of movement. The thing is that it is very fine movement. It can be used both for static and dynamic cases, that is to move or position something very accurately. It's been used for light deflection, positioning of stages in electro-optics. And the main advantage is there's no friction or backlash because the movement is really very, very fine. And of course, it's been used in valve control. Now, moving with the same basic features, if we take two elements, and here we have now the polarization need that I like to talk about in for a few minutes. And in order to, when you make a, I'm sorry, it's really bothering me here. When you just manufacture a piece of ceramic, or piezoelectric ceramic, the domains are random. So in order to organize them in a certain direction, you do have to polarize the material, and this is done by exposing it to a high field or a high voltage. Now, polarization in this case in the same direction, this is called parallel case, parallel polarization. And then when you apply the voltage for the two slices, one will actually expand, one will compress, and as a result you'll get a bending. And this can be done also with the different polarity of the polarization. Of course, the electrical signal that you feed in should be properly oriented as far as the polarization go, and of course in this case you have bending. Now, one application of such an element is the vibrating van. Here we see a piece of piezoelectric element which is connected to the rigid part by a base part. There is a van here which is just a piece of metal in this case, and then when you excite the piezoelectric bimorph element, it'll start bending, and of course, especially if you're at the resonance, we'll talk about in a minute, you can get fairly large deflections. Now, these are being used for light choppers, for example, for valves. It's been suggested that they can be used for fans, moving air. I don't know how effective it is, but at least the company who makes them, this is one of the ideas they have to enlarge the market, right? Now, here is an extension of the capabilities of the piezoelectric element. This is a piece, ceramic piece, that is used as a motor, piezoelectric motor. Now, let me just go how there are different designs. This is one design of a motor. It has certain advantages in that it needs only, for each movement, it needs only one signal. Some other motor need two signals in a phase shift. So this is just representing this family of motors. What do we have here? This is a piece of ceramics, piezoelectric element. This is just a extension, just for translating the force to a piece that will be here. So this is just a piece of, it's not piezoelectric, just a simple ceramic piece, which is glued here. Now we have at the bottom, we have a electrode, and then we have two electrodes actually, one in a diagonal way. This is one, electrode A, and then there is another one, electrode B. Now when you excite B, say, in the common, this is the lower electrode, what really happens is that this piece will move a little bit, will extend, okay? And then at the same time it will deflect. So you'll get at the end, you'll get the movement which is a little bit out and around, okay? If you excite the common with the other electrode, B, again, you'll get the movement outside, but then the direction will be to the other direction. So when you hook up a piece like this, which of course has to be mounted to a piece that can move, a stage here, then this movement of in and round is sort of pushing this stage pulse by pulse. Now this is running at high frequency, and each movement is below 1 micrometer, and in fact it can be even smaller. So it's a very, very fine movement that you can position. Now the stage, actually you can do an XY positioning, and you can use it. It's used for, in microelectronics, slicing pieces of silicon, and for electron microscope to move the piece, focus it under the beam, and things like that. Okay, the advantages of this motor is that we can get a linear motion. We can get also a circular motion if we connect it to a disc, at the outer rim of a disc, so that it will rotate, and then we get a circular motion. Very, very fine movement. It's a small size. It's used now these days for lenses in cameras. They are using these type of motors, and the advantage there is they are very, very small. And now there are also applications which are more consumer-like. For example, they started to use it for hard disk drives, moving the head, and some other application. Okay, the next family of devices that I have here is our generators. There is a lot of interest today to generate electricity on site rather than having batteries that you have to replace, etc. So if you can generate the electricity on site, then this will be advantageous. So if we have a, say, bimorph element which has some mass attached to it, say, or it has a mass, and it is subject to mechanical vibration, then this will bend back and forth. And as it will bend, it will generate electricity. And we'll talk about the model later on. And this, of course, you can harvest, as they say. You can take out and use it for electricity. A nice and interesting extension of this idea has been published recently. By the way, the numbers that will start to appear here are the paper number in the reference list. And so this is a suggestion that came out recently based on the same device. What it is, it's a small device. It's about, it's less than 1 centimeter long. It has a piezoelectric element hooked up to a beam here. This happens to be a silicon beam because the application is for microelectronics. It has a radioisotope source here, which is emitting particles here, and these particles, which are, I guess, beta, will charge this negatively, and this will be charged positive. And due to the interaction between these two charges, the beam will bend until it will touch, and when it will touch, it will, of course, discharge, and then it starts moving. Okay, so this was suggested for a small microelectronics element as part of a self-generating source, so that you can use it sort of forever. You never have to use batteries. It'll the rate is really small and the power level is small, but this is for devices like CMOS that not very high frequency, and they've actually demonstrated they can put it into a hybrid device with the microelectronics. Now, another application that is emerging now is dampers. And what it is that if you have a beam that is bending due to the fact that you have movement here, like a suspension, then you can hook up a piezoelectric element and absorb energy. By this, you actually reduce the quality factor, or the Q of the system, so it will reduce the movement, and this in fact have been already implemented in other applications. So this has been actually implemented in active suspensions for, in fact, motorcycles. You can buy a kit now for a motorcycle like this. There are skis that they have put it inside, and this will help. They are saying that this improves very much skiing by eliminating some of the vibration when you go down the slope. And of course, as far as generators, you can use it for energy sources. And in fact, at the MIT, there was a group who demonstrated you can put it into tennis shoes, and then this will actually power a small microprocessor that, of course, can be used to collect data, how much you ran, how many calories you burned, and things of this nature. Okay, so now we come to the transformer. This family is basically what we have. We have two elements, and as we apply voltage to one of them, of course, we generate a mechanical disturbance, which is sort of an acoustic or ultrasonic wave. And we actually have units like this. It's for remote control, etc. But of course, the best coupling will be when it is one one body in which you have a excitation on one side, an acoustic wave that is running through the element, and then this mechanical stress due to the acoustic wave is then generating a charge and an electric field, so that from input to output, basically we have here a transformer. The transformers come now in very many shapes. For example, this is a case of a radial vibration. There are two plates here. One is the excitation, and one is absorbing or collecting the ultrasonic wave, acoustic wave, and then generating output voltage. And one of the fairly used transformer is the so-called Rosen type, after Mr. Rosen, who thought about it. And what we have here, we have a piece in which we have two different directions for poling. As we talked about, we have one which is vertical and one horizontal. And what happens here is, as we excite this primary side, we start generating a wave inside the element, and you see here the displacement of this wave running in the element, and the associated voltage that will develop due to the fact that as this wave is generated from this electrode to one of the input electrodes, say to the lower one, we generate a voltage which is a function of the displacement here. And as the displacement at the end is larger, then of course we have a higher voltage. In this case, we have a high voltage gain, and the gain is approximately the ratio between this length and this width, so that we can get fairly high gain. Now, a better way to get higher gains is to sandwich, say, the primary in this side, and by this you get higher field. As I've said about the disc and the actuator, you higher electric field because the electrodes, as you see, are interlaced, and these are the piezo elements or the layers. So for a given voltage, you get a much higher electric field, and therefore the excitation is much larger, and then you get an extra gain factor as the number of layers you have here. So in this case, you get a fairly high gain ratio. Okay, what are the characteristics of piezo transformer? Potentially, they have low cost. Potentially, because presently the amount produced in the market is not very large. The technology is very much similar to ceramic capacitors. This is exactly the same technology. You have layers, and you have electrodes, and you have ceramic material in between. So it's just a matter of gearing up, having automatic machines to do it, and so there's nothing costly about them except the fact that the manufacturers are not geared for large quantities, and they did not develop the automation needed for low-cost production. Its compact size has fairly high efficiency. We'll see this later. Ability to work at high frequency between 50 kilohertz and say a few hundred kilohertz. It has good insulation capability because it's a ceramic material, inherently good insulation. Has no winding, so there's no magnetic field. The disadvantages are that it's a resonant device, so you have to work around the frequency, resonant frequency. We'll talk about it later. It's still low power. The highest we can go today is something like 40 watts. And of course the cost today, although the cost is really dropping down. Since I've been in this area, it's been going down by a factor of more than 10, and it's about like 3-4 years. So it's going to improve. Now, what are the applications that we have? The most popular, I'd say, application is a driver for fluorescent lamps called cathode fluorescent lamp, and this is commercial. Many laptops already have this driver. Also, it's used for LCD monitors and a backlight for LCD TV. These are the small fluorescent lamps that are used for backlighting. It's used also for ionization as ionizers. This is for the making fresh air more clean. I don't know if it's clean, but supposedly makes you feel better. Now they put it in air conditioners. For higher or larger fluorescent lamps, there are some examples, although as far as I know, there's no production of fluorescent ballast lamp, high power. I mean, like 30 watts or something like that, or 18 watts. There's no production, although they've been demonstrated it can, of course, be done. And then there's been demonstration of chargers for cell phone and laptop battery chargers, and also as isolated gate drivers. All these were demonstrated, and there are many papers on that, but they're, as far as I know, not commercial as yet. Now, the main reason that some of these are not commercial is, of course, the price. And when you compare it to an alternative and you find out that the alternative is still a lower price in sensitive areas like lighting, then, of course, the piezoelectric solution has to wait until the price will be proper. Then there are many other applications which I'm not going to go into, just to mention. There are welders, cleaners, of course. There are humidifiers or nebulizer. They are making very small droplets of water or some other material for a saturated atmosphere with water. Some are used for massage and skin scrubbers, and then ozonator for purifying water and some other purification. Yes?
Welders are usually a high power application.
Well, these welders are using huge, or large, I should say, piezoelectric elements, and they are running in the hundreds of watts power. And you usually couple them mechanically to a tip, and then you can do very nice welding, for example, for bonding wire into to a solid material, or even for, in fact, microelectronics, they do it. So the tip is connected to this piezoelectric element, and it is run at high power. I'll have some electronics for these later on when we go into the electronics part, but they are used and they are fairly high power. Right? Yes, please.
I have another question or comment. We have already 90 watts piezoelectric transformers that were applied in space application.
Okay.
You mentioned 40 watts.
Yeah, okay, but I'm talking for the ordinary person. Okay. Yeah, in space we have, these are exotic elements. They are not.
The technology of space companies is good coupling coefficient is make it possible.
Yeah, it is. Yeah, I mean, it's not, but this is not a off-the-shelf item that you can buy, and certainly, if you can buy it, it's certainly not in a price that is, compatible. Okay. Yes, please.
What about the safety regulations? Can this also be used as a safety regulation? Can you have these creepage and clearance distances of 6 millimeters or so?
Well, yeah, well, as far as I know, there's no issue of safety here, because usually the distances are fairly large, and also it depending, of course, how you what's the finish of this thing, and in most cases the distances and the voltage involved are sufficient for creepage distances. Although I don't know about the very high voltage there, and there might be a problem. But then, if you encapsulate everything and call it a module, then I guess everything is fine. All right. Okay. Now, the next thing that we are going to, according to the program I've outlined, is going into the modeling issue. Now, we need the models in order to, of of course, designed to do some analytical derivation of the electrical properties. And obviously, we'd like to have models that are run for can be run with electronic circuit simulators like SPICE and others. Now, the approach that has been used for many, many years, it's nothing new, is to use an analogy between mechanical and electrical properties or parameters, and then to apply a electrical equivalent circuit. Basically, it's called the Mason model. He was the one that actually proposed this approach. And what we do basically is translate the mechanical second-order system. This is a second-order system, which can be written as a second-order differential equation, of course. And we just translate the coefficient to electrical parameters. And the normal way of doing it is to translate mass into inductance. The losses, mechanical losses, are a resistor. The compliance, which is 1 over stiffness, is capacitance. Velocity is the current, and force is the voltage. So basically, this equivalent circuit has the same differential equation as a mechanical vibrating element, for example, an element like this. Now, in real application, we do have to connect the element to the electrical part, so we have electrodes and wires attached to them, and therefore we do have a dielectric capacitance. So this is why we'll have, in the equivalent model, we have a dielectric capacitance. We'll have a transformer which is connecting the electrical part to the mechanical part, and this is actually changing the domain from electrical to mechanical. And of course, you can reflect this part here back into the primary, so-called, and therefore you get the very famous equivalent circuit of a vibrating element or piezoelectric element, which this is the only electrical, truly electrical component, while these represent the mechanical part. Now, in reality, the elements could vibrate in many modes, like longitudinal, shear, flexural, and all these may give rise to different resonant frequencies. Furthermore, the resonant frequency could be like half a wave or could be full wave, and therefore in real situation we have many resonant elements coupled to the input. Of course, the dielectric capacitance is 1, and all these would affect the behavior if we are working at the frequency which is close to this resonant. Now, if you will look at the admittance of a, say, piezoelectric element, what we see then is number of resonant points. Some of them are multiple of one another. Some of them represent different modes. Okay? Each one of these resonant elements, by the way, we get two, like we have a high admittance, a low admittance. This high one, it would be for the series resonant, and then at some other frequency, Cin plus the inductive part at a given frequency, this branch will be inductive. So this capacitor with the inductive part will give rise to a parallel resonance, and then of course the admittance will be at minimum. Okay, so we have a series and parallel, and this will repeat itself. However, in most applications, we do work around one resonant mode, so that basically for all for many applications, it's sufficient to talk about one resonant network, and just about forget the others. No, however, there's a fine point here, and that is the following. If I look at the piezo element in which there is, again, this dielectric capacitance and all the other modes, then if you work, say, at the first or the lowest frequency, resonant frequency, then all the other are below resonance, so therefore they are capacitive. So therefore there is some capacitive addition here, and in fact, if you measure the capacitance here at low frequency, you measure all these capacitances. I'll show you this a little bit later when we talk about how to extract the model. Okay. Now, what I'm going to do now, I'm going to go over all the elements we talked about, and just to represent the model that is normally used in order to handle the electronics around these elements. And for example, here we have the actuator. Basically, it's a piezoelectric element that has this the electric capacitance and the resonant bridge. However, in these in most cases, we do work below resonance with the actuators. It's very difficult to work at resonance or above resonance. And so for this case, the inductance is sort of short. You end up with these two elements and this capacitor, and it can be then represented for a given frequency as a combination of a capacitor plus a resistor for a specific frequency, okay? So that you have, for the actuator, basically a capacitor plus a resistor, which is composing, actually, it includes both the losses, both the losses and the actual work you do. Now, the problem is, I'm going to go already in some of the problem of driving these things, is that these capacitances are very large. In the case of an actuator, we're talking about few microfarads. This is the size of a capacitance that you have to work. On the other hand, so that when you drive it, say, at a few tens or hundreds of hertz, most of the current is reactive. Only a very small part of the current is basically the one that is doing the work. So you have to gear up for a driver that will handle this reactive current. Now, in the case of a vibrating van element, again, we're talking about low frequency because the mass is large. We're talking about tens or hundreds of hertz. Usually we work around resonance, and so that basically we have this, again, simple equivalent circuit. For the piezoelectric motor, we did a lot of work on that. We are not going to go into too much detail, but let me just say that we have found that, again, around operating points that we are using the motors, they can be, this is just a SPICE or ORCAD presentation. We can describe them as a capacitor plus this resonant, and as you might see, these models are extremely good. This is, for example, some measurement done on a motor. This is the excitation. In this case, it was a square wave. Let me say this is a square wave fed through a series resistor, and you see the current and the voltage, and this will be the this will be the simulation, this will be the measurement, and the same thing if we feed it by a sinusoidal wave, we find again a very good agreement. So the models are really very nice. Now, for the damper or generator, what are the models that are used? In the case of a generator, since the current is a function of velocity, then when you move a piezoelectric, or you compress it, or you bend it, you basically have a current source, But unfortunately, you do have a large or fairly large internal capacitance. So what happens is that part of this current coming out is actually lost by the internal capacitance. And if you look, for example, at the output power that you can get as a function of the load resistance, you'll find that there is of course, for very low resistances, there's very low power you can get, and then it goes up to an optimum, and then when the resistance is high, then of course most of the current actually goes through the capacitor, and you lose most of the power. Now, as it turns out, this optimum is when the resistance is equal to the impedance of this capacitor. Now, I'll show you later on this resonant rectifier, which is overcoming this problem, and in fact able to extract or harvest more energy from a generator. This same model is used for the dampers, the ski thing that I talked about. All what you have a source, and then you have to load it in order to dampen the structure in the case of a damper. When we talk about transformers, then of course we do have two couplings. One the input, one of the output, and this is between the electrical and mechanical, and then mechanical to electrical. And then we have the inner mechanical resonance. Of course, we can combine these two together, and then we'll get this more common used equivalent circuit. Now, we like the presentation at the bottom, in which we replace this transformer with dependent voltage and current source. From the electronics point of view, these are the same. However, when in simulation, when you use this transformer, you can get into trouble. The reason is that the way in a simulation you would describe a transformer will be by putting, say, two very large inductances here. Now, for DC, these inductances are short. Now, this is not happening in the transformer. There's no short for DC in between the electrodes. So therefore, if you use it for, say, a doubler, a rectifier, you'll get erroneous results because there's no blocking. In the piezo, you have blocking. Here, there's no DC path here. Although, if you put here DC, it seems that you'll translate it to the primary, but then there's this blocking capacitor, which is actually blocking the DC. So in this case, if you put here a DC source, there's no short. Here, put a DC source in simulation, you'll get a short, which is incorrect. So this is why we like this equivalent circuit approach. Now, a common way to handle the transformer circuit in order to get, say, expression like input to output voltages, etc., would be to first of all reflect the load and output capacitor through the transformer to the primary, and then by some transformation for one, which is correct for one frequency, to replace the parallel with the series representation. And of course, this circuit is very simple now for analysis, because if you have an input voltage, you can very easily find the output voltage and then translate it back into the real voltage in the unit. Now, since the element is a resonant element, then of course the transfer ratio between input and output will behave like a resonant circuit. We have a maximum at a given frequency. This is for one particular transformer. By the way, I've noticed that here a mistake in your says W, which of course is because of the fonts, that the symbol was changed. And also I've knocked down some of the digits after the decimal point. I don't think that's accurate. So So it kind of it's, overdoing it. It came out from the calculator, I guess. Okay, now what are the characteristics of the piezoelectric transformer? Now we did some work on the generic characteristic, the general characteristic, rather than the behavior of one particular transformer. And we did it by using normalized parameters. So I'll just familiarize you with the parameters that we'll later on see. We have of course, the output to input voltage ratio. We have a normalized power, which is the output power divided by this is the input over the characteristic impedance of the resonant branch. Well, efficiency is efficiency. And then we have a normalized, well, this should be normalized load. And what it is basically a resonant frequency times the output capacitor. All these are parameters of the piezoelectric element, and the output load. So Q is normalized load. It represents actually the resistance of the load. QM is the quality factor of the mechanical part, and then C, small c, is the ratio between the reflected output capacitor and the resonant capacitor. Now, using these normalized, we can get something very nice, which is representing, all transformers. Let me start with this curve here, which is the normalized input to output voltage. Okay, and this is a function of Q, which I remind you is the load. Only it's normalized with the parameters of the transformer. And as we see is that we get an increase of the output to input ratio gain, increase in the gain. It's moderate up to this point here, which is for this particular value, and we'll talk about it, of the load, normalized load resistance, and then it goes sharply up. And the reason is that this is a point that you get a resonance with the reflected output capacitance, and you look at actually the voltage across a series resonant network. You look at the voltage across it. And this is, of course, very nice for fluorescent lamps, because you need to ignite a fluorescent lamp. You need high voltages, and so that before the lamp ignites, the resistance is very high. So you have, and you can then have very high gain, and then of course you go back to the operating point. Now, the double hump here is the normalized power. You get, for small resistances, low power, then it goes up to a maximum, and then it goes down to a minimum, and then to a maximum again. Now, the maximum means that this is the point that you can get maximum power out of the device for a given excitation, okay? Fixed excitation. With this resistance, this is normalized resistance, you get maximum power. Now, as we know, you get maximum power when then the load is equal to the internal resistance. Okay? When you have a generator which has an internal resistance, maximum power is obtained when the load is equal to this resistance. So this means that this is basically the internal resistance of the piezo. Unfortunately, at this point, the efficiency is only 50%. Because if the load is equal to the internal resistance, then it's 50%. 50% goes to the actually dissipation within the transformer. And this is a very bad point to work. So this is not a good point. The point that you'd like to work is when you have maximum efficiency, and this turns out to be this point here. Okay? At this point, you get maximum efficiency. The value depends on the transformer itself. And this is of course, the normalized. And this is the load. So for this load, you'll get maximum efficiency. The power is lower, of course, because there's no matching. But this is sort of don't worry about it, because you can of course get a higher power with a larger excitation. It doesn't mean that you cannot get power. It's just for a fixed input, you'll get more power here than you'll get power here, but the fact that you get a high power here doesn't mean that's a good place to work. On the contrary, you like to work here. So this is a very nice presentation of the behavior of a piezoelectric transformer, and we have used it a lot, and we've seen that other people have used it beneficially, because this actually allows you to properly decide, number one, if you have a transformer, what is the optimum load for it, or if you have a load, maybe it can help you to select a transformer that is proper for this particular load. Now, yes?
How about the second maximum of power?
Again, the second maximum turns...
What's the physical meaning of the load?
Well, okay. It's a good question, and it's a good question. If you look at this circuit, there are actually two frequencies involved. One is the series resistance, and when you load here, let's look here. When the resistance is rather low here, then what is operative is this branch and this load, if this load is smaller impedance than the capacitor. When you go up, then this capacitor becomes important, and then you have a different actually resonant frequency, and you can find there another optimum or maximum for the power for the larger resistance. Okay, so there are actually two modes of operation. One is this resonance, and then one with including when the actually capacitor is this and this in series. Okay, so you have, yes please.
One question of that: if I have a step-down application and the second C/0 is relatively large, for instance, then I can neglect it and I just have all this.
That's correct.
CR.
That's
but
correct.
in the other direction, I have to.
That's correct. That's correct. That's correct. That's correct. Okay. So, well, needless to say, what I'm showing has been tested, etc. I mean, it's not just a theoretical derivation, and we've tested it, and it's works out very well. Of course, some of the points here, these points are experimental points. The deviation here is because it's very difficult to do the measurement at high resistances because of the loading effects and things like that. Okay, now I'm going into the issue of model parameter extraction. Okay, how do we obtain the parameters of the model? Which are the model is really very simple. The question, what is the method? Now, basically, what we do is we do measurements, preferably by a network analyzer, and then we do parameter fitting. That is, we take the measurement and we try to fit it to the model by one method or another. However, there are problems. The problems are that the model is drive level dependent. That is, it's not a fixed model. It is changing. But that?
It's not linear.
Yeah, it's not linear. That's correct. It's depend also on the load resistance. It's non-linear in excitation. That is, actually, this is part of the drive level dependence. Some cases also, the Q is very low, the quality factor is very low, and consequently, it's very difficult to do the fitting to the second order system, because the second order system has the features nicely when the Q is high, and then you can distinguish between the parameters. If the Q is very low, the fitting is not very good. Now, most published parameters of the transformer, just a second please, are actually for low voltage, 1 volt, and for one load. So one has to be very careful applying these published parameters given by some manufacturers to the real case of a high power level and maybe different loads. Yes, please.
I don't understand. Some have low Q. What is meant with the low Q?
Well, low Q means that you don't see a a substantial increase here. It's really very, very flat, very, very flat. Okay, this will be for an actuator which is heavily loaded, for example. Transformer, usually the Q is high because transformers are, if the Q will be low, it means a lot of losses. Okay. On the other hand, some of the actuators will have a low Q because they are driving a load, and the load is reducing the Q. Okay, so transformers are really usually will have high Q. That's correct. Okay, now in order to demonstrate this nonlinear behavior, look, for example, at a case of a vibrating van. This is this thing which is vibrating, and here are the admittance of this thing, one at 5 volt excitation and one at 25 volt excitation. Okay? You see two things. Number one, of course, the resonant frequency is changing quite a bit. Secondly, you see that something here is not well behaved. This thing here and this thing here are really not like a second order system. The reason is that as you enter into the resonant here, the compliance, the capacitance, equivalent capacitance is nonlinear, and since the amplitude of vibration is increasing because you approach the resonant, then you're sort of changing the resonant circuit, and gives you a different behavior. Of course, with the phase, you see the same, of course, shift corresponding to the amplitude. Also, for example, a transformer, if you run it at 2 different output voltages, you see that the resonant frequency is changing a little bit, and also the gain is changing a little bit. And also the same transformer, same excitation, but running a different load, with different loads, you see quite a bit of a change in the resonant location, as well as some of this peaking that I was talking about. This is obviously something nonlinear going on with this strange peak. So what do we do about it? Well, normally what we do, we fit it to the area that we like to work at. For example, this will be a experimental, will be the round the circles, and the dotted line will be simulation using the model that was fitted here. If you fit the model here, then obviously for different load resistances it will not be good. Now there is some work going on in trying to develop a nonlinear model for piezoelectric transformers. We are doing some, and some other people are doing. I'm not going into it because unfortunately we don't have, and I don't believe some other people have substantial results. But this is a subject that is really an ongoing research in order to try to better find a model that will be usable over a wide range of drive and loading, etc. So what we can do now, we can do a fitting around the area that we are interested in. That's the best we can do. Okay? So typically what we'll do is, if we start with the network analyzer, obviously no way will the excitation of the output will be sufficient. Okay, we're talking about high voltage. In some cases hundreds of volts. So you do need an amplifier. Okay, you do need an amplifier. We do need an amplifier, and then you feed it to the element, say in this element, and then for the reference channel, you need a voltage divider, and if this is like we have a 50 ohm network, then the 50 ohm is part of this network divider for the input. And then at the output, say if you like, this is for measuring the impedance, okay? This is voltage and current. So you pass the current through either the 50 ohm or a shunt. If the currents are high, then of course you have to protect the input, so you put a shunt here. So by this, you have high excitation, you measure the input, you measure the output, and of course the ratio between you measure the voltage and you measure the current. and then the ratio of, say, current to voltage is the admittance, and you can do it at any power level that you want. And here is an what's that? Okay. The point of this slide is that we can do a fitting on any part. It's very difficult to do fitting for the whole thing because then you'll have portions which are well fitted and portions which are not. But for small parts, you can do very well fitting. It turns out that the model of the RLC model is very flexible, and you can fit it to just any shape. But it doesn't mean that it really has a physical meaning to the parameters, but as far as fitting and getting the model, then it's okay. So, for example, if we want to do a fitting for this resonant blade device, and as we have said, we do it around one particular resonant frequency, and notice that the capacitance that we are measuring, that we have is, as I've said before, earlier, we have the input, the dielectric capacitance, plus these capacitances, because at a frequency which is lower than these resonances, the inductor is short, and then we basically have, I'm neglecting here this resistance, so we do have the contribution of the capacitance, okay? And then we have these parts, and we can then do some measurements and do a fitting to this part. There are various ways of doing it. And here is a typical sort of blown admittance curve. You see, this is the capacitance at very, very low frequencies. This is what you measure, say, with a RLC meter, okay? And as you go beyond the first resonant frequency, notice that this straight line, which represents capacitance, okay, a straight 20 dB per decade is a capacitance. This capacitance is going down by a bit because at this point we are losing the capacitance of this resonance, because we are now at a frequency which is above the resonance, and therefore the impedance here is high already, because the impedance of the inductor is large, so we don't see this extra capacitance. And so here basically we can look at this is pretty much the total capacitance excluding the first one, okay? Here we have all the capacitances. Beyond this we have all the capacitance including this one, and then we'll have excluding the other one, okay? So we can then use this point in order to get the estimate of these capacitances. There are two ways to do it. We can either look at the imaginary part here and from this to get capacitance, or assume that this is a straight line and then just do the capacitance measurements from the impedance at this particular point. Okay, so this is a fine point. Don't worry about it too much. It's just improving the fitting. Now, next thing we can do, if we are talking about a certain range, say if we want, say, a range frequency below resonant, in this range, the equivalent circuit is like this. As I've said, the inductance is a short, so we have some capacitance and some resistance. We can break them into the dielectric capacitance and the other capacitances. We know that this is actually a series connection, and then by certain manipulation we transform it back to the resonant thing. So what we basically do, we start by measuring a certain portion. For example, this portion here, we measure it. We fit this portion to this RC network, and then by these manipulations extract all the other parameters. Okay, so this is one way. Of course, then you can do a least square fitting. I'm not going into it. Just looking at all the values, comparing them to the equation, and then extracting the parameters. This is just some examples of this method. You can see very nicely that you can, for example, in this case, this is a frequency above resonance. You can very nicely fit area that you are interested in. You get it very nicely. In the case of a transformer, the problem is that in some papers, in fact, the model was obtained by shorting the output. If you short the output, you have just a circuit which is basically this circuit. Because if you short the output, then of course you don't have all the capacitance of the output, and you have this thing. Unfortunately, when you short the output, you change the operating point considerably. And we have found that the model that you get is very much different from the model under the real operating point. So this is not a good practice if you need a very fine model. The best thing to do is, again, to do the fitting under the real operating condition. So again, here what we do, we feed in, we load it. Actually, RD2 is the load of the piezo in this case, and we feed in the signal, and then this is really for the forward, and then we do it the other way around, that is, we feeding signal from the output back into the input. And it turns out, well, I'm not going to bother you with all the details here, that you can write two equations for the two cases which are related to the phase that you are measuring. And we have found that the best thing to do is a fitting to the phase. And here you see that this is the phase and this is the fitting. And when you do this, from the parameters, you, again, as I showed you before, you can extract the parameters of the model and eventually end up with a model which is very, very nicely fitting your transformer over, an extended area under the real excitation. Okay, this will be like under the, say, few hundred volts or whatever that this transformer was designed for. Yes, please.
One question to this part. This model is always correct under different load conditions and under different input voltage
That's correct.
conditions.
That's
All
correct.
parameters.
That's correct.
But it is not true if I consider the higher harmonics to being a nonlinear aspect. Or how do I understand nonlinearity?
Well, it's not. I don't think it's a question of the higher harmonics. It's a question of the fact that they say the compliance, the stiffness of the element is dependent on the stress that it's under, and also the displacement. The larger the displacement, the more nonlinear is the stiffness. So that this is a nonlinear phenomena, and we do not know. We don't know, at least, how to describe these effects on the physical parameters. So this is what we are lacking. So we are assuming that this is the compliance or the stiffness is constant, and it is not. It is changing. Okay. Okay. We are moving ahead, and we are getting into issue of drivers. Unless there are some questions up to this point, gentlemen, if there's something, please don't hesitate. Okay, we are, by the way, according to the program, we're going to have a break at, if anybody wonders, at 3:25. Okay, at 3:25 we're going to end. I guess they're going to have coffee and beverages outside. Okay. I'm not going into the area of drivers. That is, how do we drive piezoelectric elements? And again, we'll go over the various elements and see what the solution that people are using for these drivers. Now, the main issue that we have are the high input capacitance. That's a real problem, because the reactive current is very large, and therefore the circulating current is large, and if you want high efficiency, you have to do something about it. In many cases, you also need a nearly sinusoidal drive. This will be mainly in the motor area. The harmonic distortion allowed is very low, and you really need a sinusoidal wave. And to generate a pure sinusoidal wave at high frequency, well, takes some effort. And then, in some cases, we need fast response. That is, we want to change from one mode of operation to another. So these are the main problems that one has to overcome. Now, if we look at the general case, for example, for a transformer, the problem of the input capacitance is, of course, that if we don't put anything in between, and we just drive, say, with a half bridge, the piezoelectric transformer, then obviously we are going to have hard switching because of the large capacitance, and therefore, of course, we'll have noise and losses, etc. Now, the preferred way, of course, is to use the soft switching, and this has been one of the major issues that people have been working on, of course, with other topology, and I describe your work too, Matteo, because this is really one of the major issues here. Now, let me start with, again, I'm going over the various elements so that we'll have the full picture. Actuators. Well, actuators have extremely high input capacitance, really very high. We are talking about few microfarad. I can tell you that I've been working lately on an actuator that is used for optoelectronics device. It has 6 microfarad capacitance. The current, it has to be run at relatively high frequency for this capacitance, something around 1 kilohertz. So the current is, say, half an amp. Half an amp for the reactive current. The real current is maybe 20 milliamp. This is the whole thing. So most of the current is really capacitive, and it's a big issue of what to do with it. Okay? Now, in most cases, there is a need for DC. In the case of actuator, DC to low frequency, there is a need for good tracking, high accuracy of gain. In most cases, we'd like to have low ripple on the voltage. The reason is of the high capacitance. If you have a very small ripple on the voltage, then the current of the ripple will be very high because the very low impedance that you have for this large capacitance. And the voltage range we are talking about is between 100 and 1,000 volt. This is the range that, say, commercial actuators are working. Now, there are two actually ways to do it. One is the old way with linear amplifiers, and one what people in this area are calling charge recovery method. Well, charge recovery method is nothing but Class D amplifier. I'll talk about it. And this is a switching amplifier that is used, and it's called charge recovery because the reactive current is really pumped back into the bus of the driver. Okay, now the classical method, of course, is to use a Class AB amplifier. And the problem is, of course, let me see if I have it here. The problem is, of course, that the efficiency is very, very low. Because, as I've said, the currents are very high. The voltage that you need is high. At best, for the optimum waveform, you can get around 50%. But in the real operating region, you get maybe 5 to 10% efficiency. So it's really very bad. And these are getting extremely hot. Another problem, which is a little bit off what we are talking about, but let me just point it out, there is a problem of stabilizing these systems dynamically, because they are highly capacitive, so therefore you have an extra phase shift, a lag phase shift, and then when you take a feedback to the input to get good tracking, you may run into problem of low phase margin and therefore oscillation. So these are really not simple units to work. There are some companies who make, of course, these special amplifiers for piezoelectric elements, and they're very costly, I can tell you that. Now, another way is to use the Class D, which is basically a PWM inverter, which is modulated. It's running at high frequency, high carrier frequency, high PWM frequency, in order to generate the low frequency that you need here. Again, actuators do not work at high frequencies, they work at fairly low frequencies. Say 1 kilohertz is just about the limit today. So basically you have an inverter that is generating these voltages. You can run it at fairly high frequencies, say 200, 250 kilohertz. This is what is done today, and to generate, say, 1 kilohertz. So you have a nice waveform at the after filtering at the output. The problem is that you still have some ripple, and this ripple generates fairly high ripple current in the device. But in simple application, this is a good solution. In a recent work, not ours, this is by others, you'll find it 26, they have compared 3 different drive methods for a piezoelectric element of this kind. One is using a LC network. This is a resonant. One using a LCC that is with 2 capacitances, okay, relying on this capacitance and this inductance here. And one pure PWM, which is, as I've shown before, Class D amplifier. Okay. By the way, this particular paper is really dealing with a welder. Okay. So here is a case of a real problem. And the power level, if I correct it, if I remember right, is indeed few hundred watts, like 300 watts or something like that. Now, what they have found is interesting, that if you compare the inductances, then you find out that for the PWM, you need the smaller inductance for the filtering, as compared to the resonant structures. For the resonant, the reason is very simple. You run the PWM at 250 kilohertz, so you need the filter for very high frequency, while in the resonant configuration, the L is part of the resonant for the low frequency, so therefore the inductance is high. So that in this respect, the PWM is the most compact among the various possibilities. Unfortunately, they don't give much information about efficiencies, and I bet that the PWM efficiency is not very good, because running at 250 kilohertz, and this is hard switching because you have this reactive current coming in. This is the phase is not it's not high frequency. It has a low frequency component like a regular. So probably you lose in the efficiency domain. Okay, now I turn now to the other low frequency devices that need normally low power, usually constant frequency, and usually you would like to work at around the resonant frequency. Now the problem is that the resonant frequency may change, and you may wish to use like a phase lock loop in order to lock to the frequency. Now we have examined various possibilities. One is to use a simple square wave for this type of devices. The problem that you have is that the current is extremely noisy, because you generate these high frequency components, and you have this hard switching, of course, at each time, and this would be very difficult a signal for phase locking if you'd like indeed to track the signal. Sinusoidal is the best thing. Unfortunately, sinusoidal is not very simple to generate at low frequency. Okay, So it has many, many nice features, but it's not very good. And it turns out also that if you would like to, say, use a resonant circuit, because of the very low frequency, you need extremely high inductances, which of course are not realistic. So we have found that the best drive for these is really a trapezoidal type of a waveform. And what happens here is that the current, you get a high current during the transition, but then you get only the sinusoidal waveform coming off the resonant circuit, and this is very easy to lock to a phase lock loop. So this is recommended, and in fact some companies who are selling these devices have this type of driver, which is really very appropriate for these elements. Motor drive. What are the requirements? The requirements are fairly high frequencies, ranging between say 30 kilohertz to say 150, 200 kilohertz. A sinusoidal drive. Usually it's a constant frequency operation. You work at a fairly constant frequency and you just change the amplitude. And you need fast response to stop, etc. Now, as I've already said, the same Mason equivalent circuit is applicable to the motors. Again, around the operating point, it's approximately a capacitor and a resistor. And this you have to drive now with a sinusoidal waveform. The most, as a classical way of doing it, is to start with a square wave, to filter it out, to work very close to resonance, so that you'll have nice filtering of the square wave, and then to feed this waveform to your element, to the motor. The problem is, there are a number of problems. One, as I've said, the efficiency will be very low. The reason is that you have reactive current flowing through the switches here. And this reactive current is many, many times larger than the actual power or current that is associated with the power. Another problem is that if the capacitance is changing of the piezo, or due to cabling, for example, you lose the resonant point and you have to retune it, okay, all the time. So consequently, there is a sensitivity to this capacitance. Now, we have been working a lot with this so-called push-pull parallel resonant arrangement for driving actually piezoelectric motors. This represents the motors, and here we have a resonant, in this case a parallel resonant. Sorry, I lost it. Okay. This inductor of the coupled inductor or transformer plus this capacitor is a parallel resonant circuit. We drive it alternatively, one transistor then the other one, like in a push-pull, of course. And it is current driven, namely there is a inductor in series with the input. Now, a circuit like this can work in three modes. One is the mode in which the switching here is exactly at the resonant of this tank, and this will be, in this case, get nice sinusoidal waveform. I'm like, for example, on the drain of the transistors. Another mode is when the frequency of the switching is smaller than this resonant, and what happens is that the resonant is finishing, or the resonant cycle finishing before you have the switching, and then the diode actually is capturing and you have a current through the diode. This will be this case. And the other case is in which the switching is larger, and then actually the resonant doesn't finish and you start the commutation again. These two will cause very high losses, and you would like to work at this point. Yes, please.
One question on that. Additionally, there could be a DC current at the input of the transformer. Is correct?
You mean here?
You do not have accurate equilibrium between the two switches. There can be easily occur a DC current.
Well,
is this a problem, or is it easily to handle?
no. This may be in a case that you have two inductors, okay, and two switches. If you have here two switches, okay, what you're saying basically is that if you have, say, one the duty
cycle is different.
Okay, it's not like 50%.
Yeah.
Okay. Well, obviously, if the duty cycle is not 50%, then like you have a residual DC. However, what really happens is that the waveform will adjust, and you'll have one larger and one smaller swing here, and then this will actually compensate for this offset. Yes, please.
It will be a real problem if you would neglect the L-in. If you have a voltage
That's correct.
set, then you
That's
really
correct.
get into
Yeah, that's correct.
the unbalanced
That's correct.
condition.
That's correct. If you have an inductor, then what will happen is that you'll have a non-symmetrical between the two sides, and this will actually compensate. This will do the reset. Actually, the reset will be automatic. Okay. Now, so the problem that we have here is that the operation of this circuit is optimum under the specific case that the switching frequency is the same as the resonant frequency. And if the switching frequency is different from the resonant frequency, either higher or lower, then obviously you will have distortion, and you will, of course, lose soft switching, and then the losses will be higher. Yes, please.
Well, you mentioned that both of those, the boost and what you call hard switching, is not good. But well, as I see it right now, the boost period is not that bad, because like the body diet's conducting, so you still have the zero voltage.
Yeah, in this case you do have zero voltage switching. That's correct, but you have a large circulating current.
Oh, I see.
Well, this circulating current is the inductor current, which normally these transistors don't see, because this is usually circulating here.
Okay.
So they don't see, they just see the real input current associated with the power.
Okay, got that.
Okay,
Yeah.
and these will be high power. So what can we do? Well, there is a solution to that, and that we have implemented, and it works very nice. There are two stages here. One is this little circuit, which is, by the way, commercially available, and this circuit here will synchronize the switching to the resonant. It'll automatically switch the transistor whenever the voltage goes back down to zero. So this will lock all the time to the resonant of the tank. So that's good. The problem is that if you don't want this resonant frequency, you want another frequency. So what we can do, we can use a control inductor that we can bias it at the outer rim. This is the inductor, has a gap inside. There is no gap at the outside. And these are bias windings. So you can change the inductance by biasing this. The power involved is very little, although the current is a little bit high, but the voltage is very, very low because it's a short circuit. And when you do this, you basically change the inductance. So here, what this circuit is doing, this runs automatically to adjust the switching to the resonance. Okay? Now you measure the actual switching that you have, switching frequency. You compare it to the frequency that you want. The difference by a phase comparator is feeding actually a buck modulator, PWM modulator, that is changing the bias of this element. So by this frequency, the switching frequency, will follow the input frequency. And it will follow it by changing this inductance so that the resonant circuit will be exactly the frequency that you want. So this is automatically will follow it. And you can change now, for example, you can either change the frequency or you can change the capacitance. It will also adjust. If you change the capacitance, then immediately this frequency will change because this is locking to the resonant. Now the resonant is different. It will comparing to the frequency that you want. It will generate a bias current to push this thing back and to change the inductance so that to create the right resonant frequency which is equal to the one you want. Okay? So this circuit overcomes this problem and it works very nice, and this has been implemented for actually a piezoelectric motor that really needs different switching frequencies, etc. I think this is probably a good place to have a break, 3:25 on the dot. So we'll, according to the program, we'll start again at 3:45. So you have a 20 minutes break. There's, I guess, coffee outside, or it's waiting for us. Okay, thank you. Okay, what are the requirements for the transformer drivers? Frequencies we are working today is between, say, 30, 50 kilohertz to a few hundreds. We would like to have a low distorted drive, although it's not necessarily. Of course, we'd like to have soft switching. In some cases, we need some gain because the transformer itself has not sufficient gain. We need to be able to regulate the transformer over a power range. That is, because in application the load is not constant and it is changing. So, for example, in DC to DC, the load, of course, will change. In the case of ballast, we may wish to do some dimming. So we'd like to have a range. And in the case of ballast, we would like to have the ignition voltages available without extra igniters, etc. So, as we already said, doing nothing will bring about hard switching and, of course, high spikes and losses. And the thing that we'd like to do is, of course, have soft switching. I'm showing here half bridge, but of course there are some other topology we'll talk about. Now, the most elegant way, of course, is to be able to drive directly the PT and to utilize the fact that it is a resonant circuit, and under some operating conditions, you can see here an inductive behavior. And if you have an inductive behavior at the input, then of course you can have soft switching because you have a lagging current, and this will be sufficient to charge and discharge the capacitances here at the half bridge. We did some work on that, and here we see what we'd like to get if indeed we have a inductive behavior into the element, including the input capacitance. That is, the inductive behavior should overcome this input capacitance, and net result would be a inductor of low enough impedance to carry the current needed for charging and discharging the capacitors. Then we'll see, of course, that self-commutation, this will be the gate drives, and during the daytime will be we'll see the self-commutation due to this lagging current, charging of the capacitor, and of course, in this case, we'll have soft switching, and the diode will conduct, etc. Now, the problem is, of course, that you do have to have sufficient current so that the resonant circuit, the equivalent resonant circuit, that is this inductor plus the total capacitances, will be able to change this voltage, and this time is approximately a quarter of a period, of a resonant period. So the problem is how much current can you get here when the behavior here is inductive. Well, as I've said, we did some work, and there is the reference here, 32, and it turns out that it's pretty much limited what you can do. It is possible, but it is limited. What is shown here is, this is the quarter of a period needed for self-commutation. That is, in order to have a self-commutation, the voltage should increase at least to the to be within a quarter of a cycle. Otherwise, it sort of continues. Okay, and so all the curves below this range are providing soft switching. Again, the analysis here is in the normalized parameters that I have mentioned earlier. So Q stands for the load or normalized load resistance. Okay? And what you see here, that you can get soft switching if you lower the load resistance. This would be the normalized one. And then you get a fairly large operating region. This is frequency, normalized frequency. Okay? One is like the resonant, the mechanical resonant frequency. But what you lose is efficiency, because if you need more current, you need more reactive circulating current through the device in order to provide soft switching. This current with the internal resistance of the device will cause losses. So by increasing or requiring more inductive current, you automatically increase the losses. This is a payment that you have to do. And as you, of course, increase the resistance, the range becomes smaller, and then until it vanishes. This is for one particular transformer, and it's not guaranteed that you can do it for any transformer. So this is very, very tricky. I mean, it is possible, it has been shown, but it is tricky, and in some cases you can do it, in some cases you can not do it. In any event, you simply lose efficiency. You see here for this particular element, if you just walk at this borderline, you have a fairly high efficiency, and here you go the drop by 7%, which is of course a lot. So, okay, as I've said, this can be done, and here is an example of actual circuit that was operated this way. You see here the resonant, the half, as I said, the quarter of a period. Here we see the diodes actually conducting, and this is the switch part. Okay, this is one switch, and this is another switch. This is just a bipolar drive. Okay, so the advantages of this thing is that it's really simple. It's relatively, of course, low cost. You don't have to add anything, but it's very tricky. The operation range is small. You do not operate at the optimal point. You cannot use it with all transformer. And also, what is important is that the waveform you get is really not sinusoidal. This is the waveform that you get at the input of the transformer. And you can generate some higher frequencies. In fact, this is probably part of it. So that this is really not the optimum waveform that you like to feed a piezoelectric transformer. you'd rather have it sinusoidal wave, but at least less squarely like here. Yes, please.
One question on that. We have investigated this from the side topology as well, not so much from the transformer side. Do you believe that between the several construction principles of the transformer, like let's say thickness mode vibration with a ring, or let's say rectangular length and a radial, are there significant differences in the efficiency reduction that you have
Yes.
mentioned?
Yes, absolutely.
What do you believe is the radial transformer the best one to use?
Well, I don't know. The radial transformer is being a bulky type of a element, and apparently the Q of it is very high. Then you need a very small deviation from the frequency to already get into the inductive behavior. While if the Q is smaller, then you have to go to a larger deviation of frequency. And this is probably what makes it a little bit more suitable for this thing. And as we know, some papers, Professor Lee group, etc., show that with the radial they get a pretty good result. But there's no question that compared to the case in which you do not use this inductive mode, the efficiency will be higher. There's no question about that. Okay, so on also a point to take into account, as I've said, it's a trapezoidal waveform. You don't have a voltage gain. Sometimes, as I've said, you'd like to have an extra voltage gain because the transformer is not, the gain is not high enough, and your bus voltage is not sufficient, so you'll got to have a little bit of a boost, and this is not provided here. So the other option is to add a inductor, and the way to do it, there are several ways to do it, and here we show the parallel connection. You can put an inductor in parallel. Obviously you need a capacitor in order to block the DC, because in a half bridge you have a DC component here. Or you can put a series capacitor here and then put the inductor so that you have decoupling of the DC. Now, in this case, what you do, you just generate a reactive current through this inductor, and you use this inductive current in order to commutate the half bridge, let's say, in this case. And this, of course, depends on the size of the inductor. You have to size it so that you have sufficient current to charge and discharge these capacitors. Okay? It's a nice solution. For some reason, people from Japan like it very much. Most of the papers, they use it. The only disadvantage that I can see is that, again, it's not a sinusoidal, or it's not even approaching a sinusoidal wave. It's like a trapezoidal waveform, more like a square wave. And this could be, in some cases, a little bit of a disadvantage, because it could generate higher harmonics depending on where the, of course, the other modes of resonance rest. So this would be the main problem. Yes, please.
About EMI, the inductor is in parallel to the piezo transformer, and so the higher harmonics generated from the piezo transformer itself be broadcasted to the input. So it is not only very good in EMI, or is it better than the series inductors?
Yeah. Well, I don't know about this point that you which is pointed out, which is really interesting, about this, back injection into the line. There's no question, however, that you do not have the buffering effect of a series inductor, which is, in this respect, either way, to the piezo and back, obviously a better filter than having this parallel thing. Okay, so now comes the option of putting the inductor in series. Now, it's really simple. Conceptually, you just put a inductor, and by this you get a reactive nature, and therefore you can generate this lagging current that you need for charging and discharging the capacitors. The thing is that choosing this inductor is not simple. It looks simple, but it is not. The reason is, I'll show you, that there is some interaction between this inductor and this capacitance, the dielectric capacitance of the transformer. You do not want to work at a resonance between Lin and this capacitor, because then you may have some very erratic behavior. That is too dangerous. Also, you may generate very high voltages on this capacitor. So you don't want to work at this point. You don't want to work at a very different frequency, or too low or too high frequency related to this resonance, because obviously if you go to a very high frequency as compared to the resonant frequency, you'll have attenuation here, because this is a low-pass filter, and if the frequency is very high, you have attenuation. So this is like sleeping with a very short bed, and you can either have your head in and your legs are sticking out, or you can put your legs in and your head is coming out. It's we have found that in the general case, it's very difficult to choose the right inductor, even if for simple cases. Now, let's start with the input impedance of the PT. Okay, if you look at the input impedance of a PT loaded, okay, you'll see that this is shown for two different transformers. Okay, this is not V out over V in, I'm sorry. This is the input impedance. Please correct it. This is mislabeling here. This is not correct. This is not correct. This is not correct. So the operating region, oh, I'm sorry. Forgive me. This is correct. This is correct. The phase is of the input. Okay, the phase is at the input, while this is the output to input, to see where is the operating region. Okay, the operating region of the transformer is this frequency here. Okay, what we see is that in the case of this particular piezoelectric transformer, we get some change in the phase, but it's not very large. Here, on the other hand, we have a large change in the phase, and notice that it is so large that, say, in this region, it's already inductive. So that really at the operating region, the transformer is not capacitive. Although it has a input dielectric capacitance, it is not capacitance. So this is why it is very difficult to sort of do a estimate by analysis, and probably the simulation is the best way to go, and this is what we have found. So here's the situation. This is the operating region of the transformer. This is again output to input ratio, just to see where we are at. This we have different input inductances. This shows the phase of the series inductor current, and obviously you like it to be lagging, because this is what you want for soft switching. Okay? Now, if you look at the overall input to output ratio, that is from your bridge to the load, that is going through the inductor and then the piezo transformer, you see that for different inductances, you have quite different responses. In some cases, you do have attenuation. This is, by the way, where you get resonance between the inductor and the input capacitance of the piezo. But this is not the place you like to work at, because this is not an operating region for the transformer at all. You get very high voltages. Actually, it can damage the transformer. You get very little output out of it because this is outside the resonance. So you like to work here. So among these, there is like the blue one, I think, or actually the if this is the region, the black, excuse me, the black one seems to be the best one in terms of giving you a better gain. But still, in this particular, for this particular piezo, you lose gain. The one would mean that it was 1-to-1, and here you actually lose gain. What I'm trying to, this is not really a solution to the problem. This is just showing that there is a problem. And it is not a simple thing to find the optimal series inductor, inductor to the piezo transformer. And as you'll see in most papers that people have been using series inductor, they did it by trial and error, and that's what you end up actually doing, and you just select one. This is really something that still awaits a good analytical solution to the problem, to find a elegant way to choose the inductor in a orderly, simple, analytical way. Here are the typical waveform that you get. This will be the inductor current. This will be the voltage across the piezoelectric transformer. This is for the three inductors that I've mentioned, the 1.6 or what is 2.4, 1.6, and 1 millihenry. And as you see, the waveform are not too bad because you have a fine filtering, so that the waveform is not bad at all. The current is far from being sinusoidal, though, but it's okay. There's no problem in that. And here we see the soft switching effect. And what you see here, that among the three, the blue one, although it's inductive, is insufficient. It is not actually doing the soft switching. It's not self-commutating the voltage to the end. In fact, only the green one, which is 1 millihenry, is good enough. So if we go back to here, and we see that the 1 millihenry is the one, so this is the one that we are closer to the resonant. I don't know what it means, and actually it seems to be the optimal value in this case. So I have no really good solution to the problem that I can show you, except to say that it's not trivial, and you really have to work in order to find the inductance that is needed. And I wish somebody will work on this and find a good solution to the problem, analytical solution. Now, another option to use is to use a clamp driver. Now, the idea is here the following. As we have said, you don't want to work at a resonance because of the high voltages that you'll generate. And however, if you put a diode that will clamp the voltage here, you can approach the resonant without endangering the piezoelectric transformer. So this is this idea here, and here is, for example, the result. We've been using it a lot, especially in experimental setups. It's a very, very nice solution. You see here, this is the voltage, and what happens here that the sinusoidal wave is building up, and then it clamped to the bus voltage and then to ground. So you do have limitation of the voltage. You are not afraid that you'll get very high voltages, and of course you can adjust it to be in the area that you are interested. In this case, you have a nice inductor current, and you have, of course, in this case, soft switching. So this is a possible solution. The disadvantage is, of course, that in this scheme, during the clamp time, there is a circulating current here, so you lose some efficiency. So you have to be careful not to build up too high a current so that these losses will be high. So this has to be, what has to be chosen carefully is actually the characteristic impedance of this total capacitance and the inductance, so that the impedance will not be too low as to generate high circulating current when the diode is clamped. Okay, another approach is the Class E amplifier that has been used and demonstrated, and it has nice features to it. Here we see the inductor, the switch. This is the anti-parallel diode. This is the piezo element, and this is the load, everything reflected to the primary. And the nice feature is that it has only one switch. It's really simple to implement, and of course the sinusoidal waveform lend to a better EMI suppression. However, what you pay for it is that you have a rather small operational range, because if you like to change the frequency or if the load is changing, then the soft switching condition of the stage is altered, and you may not have an optimal operating point. And another disadvantage is that you have high voltage stresses, okay? So that because you obviously generate a high voltage here, higher than the Vin, and if it is a line, say, offline operation, then the voltages may be very high. Maybe you'd like to add something to this, okay? Okay. Only good things.
We wanted in the morning to demonstrate that the opposite is true, that the operation range is large. But of course, it's very, very tricky to track the duty cycle with the frequency.
That's correct.
And that is a complicated
The control is control is complicated.
The control is complicated. Rather should sound complicated control, and the design parameters has to be made very, let's say, accurate in agreement with the application. On the other hand, you are right. You cannot cover a very large output plus one large input
That's correct.
with one and the same parameters.
That's correct.
You have to jump out into the
That's
next
correct.
one.
That's correct. That's correct. Okay. Now, other possibilities are actually the two-inductor version of the push-pull converter, and basically this is something we have talked about, although it looked differently. This is rather than one inductor and a parallel network, we have two inductors, but the operation is pretty much the same from the analytical point of view. You have one transistor conducting, you have current coming in, you have a frequency, a resonant building up, and then you switch to the other one. Of course, here you have to be careful to have, not to have a dead time, but rather overlapping. That's okay, but not the dead time, because then, of course, you'll have an inductor with current which has no conduction path. But, and this is again has been demonstrated, some Japanese workers have demonstrated this. Again, the disadvantages are that, again, the operational ranges are not very large, and this is because if you like to keep soft switching, then you're pretty much limited to the resonant frequency. The other version, which I talked already about, although with another application, is the push-pull. It's basically the same thing as the two-inductor, except that it uses a split inductor with a center tap, and these two transistors are working, and so that in general it's the same. We talked about it, and I guess there's not much to add to it. One more topology which has been demonstrated, and it has some merits to it, is to use a forward flyback arrangement. So basically, it is similar to the Class E, but not exactly. Okay, and the difference is that you have powering in the two stages. That is, when the transistor is on, okay, then you have like a transformer with the inductance feeding the output. Okay, so there is power coming in. And then when the switch is off, the power which was accumulated in this actually magnetization inductance is then fed to the output. The resonance is between basically the leakage and this input capacitance. This was shown for various applications. We have used it for a driver for a cold cathode fluorescent lamp. And this is, although it shows many windings here, this is obviously a one sort of, call it integrated magnetic sort of. Basically, it's two windings on a core. So the LM is the magnetization, while the leakage, L leakage is of course the leakage between these two windings. Okay, so this was used in order to boost up a 5 volt to fairly high voltages needed for, this is a bulk single layer Rosen type transformer that needs fairly high voltages around 100 volt. So that from the 5 volt we generated about 100 volt or 50 to 100 volt, and then of course the piezo boosted it up to, I guess it was 600 volt or something of this nature. And here are some typical performance of this thing. This is the efficiency measured, and these are the illumination. And you, by changing the frequency, then, excuse me, by changing the duty cycle with a fixed frequency, you can change the dimming. And here we see actually the dimming effect. Okay, the operating point, I guess it was something like 5 or 6 milliamps. Okay. Few words about the power control. In order to control the power through a piezoelectric transformers, there are many things that you can do, and all of them, of course, have been explored. The most natural thing is to change the frequency, because it's a resonant element, it's like a resonant converter, and you change the frequency, you change the power level. However, there is merit to use PWM because in some applications you do not want to change the frequency too much. And in this case, there are a number of things you can do. You can either feed the PWM into a resonant converter and then go on into the piezo. You can use asymmetrical half-bridge. I'll talk about it in a second. Oh, sorry. Or you use a low-frequency PWM, sort of a on-off. That is, to run it at a carrier frequency and then to turn it on and off with PWM. And this is done for dimming very frequently. Actually, many commercial drivers are working this way, and they are running at a carrier frequency, and then they turn on the lamp on and off by PWM on the carrier. Okay, and then there is a combined, of course, PWM and frequency modulation or pulse modulation, doing both PWM and frequency modulation. There are some papers on that. I'm not going into it just for the sake of completion. I thought that I'll bring this. Although the active clamp example I'll demonstrate here. An interesting, I think, approach is to use a active clamp arrangement in which you turn on and off, and you then build up voltage on this capacitor. You see, you have energy storage element which form basically a resonant circuit with this capacitor. So when you turn, say, this transistor off, this current is going into this capacitor and building up a voltage, which could be, of course, higher than the input DC. Okay? So in this case, it turns out that the voltage that you generate across the capacitor has this form, and the features of this thing is that you have number one, zero voltage switching. Number two, you have a voltage gain, and the reason is that you build up voltages which are higher than the input voltage. The sort of disadvantage is you still get something like a square wave, because you when the transistor is on, you feed basically the input, and when transistor is off, you basically feed in the voltage of this active clamp capacitor. So this is the kind of waveform you get at the input of the transformer. Of course, you can put a series inductor, but this, as we said, is not a simple thing to do. Anyhow, you can sort of use it to a little bit smooth out the waveform rather than using a square wave. Now, what you get here is rather interesting. If you'd run a half bridge in an asymmetrical wave, that is, one in Q2 is on and Q1 is on, without this capacitor, just a half bridge, okay? Then you get a maximum at duty cycle of 0.5. So that the input to output ratio is something like this. You get a maximum transfer, voltage transfer at 0.5, and then it's from 0 to 0.5. This is when the upper transistor is working, and then you have the other half. If you use the active clamp, however, because you are building up a higher voltage, you sort of keep going with the output voltage, and you actually generate higher voltages, so that it's nice that you get the full range, and in fact, as I've said, the gain factor on the piezo element, which is kind of a neat way to go. This is, again, some people, I guess Professor Ninomiya and some others worked on it, and these are the reference here. That's not our work.
That's because it turns more like a boost circuit?
Sort of. You might say, you might say that this inductor and plus capacitor is actually adding some voltage. That's correct. That's a nice way to look at it. Yeah, I agree to that. Right. Okay. I'm now turning to the question of rectifiers. Now, if we are talking about a transformer or another source, piezoelectric source, like a generator, usually we like to have DC, and therefore we do have to rectify the AC, which is coming off the piezo. Now, there are a number of ways you can do it. You can do it, first of all, with inductive filters, for example, shown here. And this is like the regular half-wave rectification. The only thing is that with the piezo element, because of the reason I've already said that there is no DC path here, you do have to add an inductor. Without an inductor, this thing will work, because there's no in this arrangement there is a DC coming off here, and obviously with no inductor, this DC will have to sort of charge up this capacitor, and that will be the end of it. So you do need an inductor. This it may be not a very nice solution, just having another inductor. What you can do is you can use a current doubler, in which this inductor, which is providing the DC path, is in fact part of the filter. Okay, so you don't lose as here that you actually need two inductors, and this is a nice arrangement that you can rectify the AC coming off the PT. Now, an analog solution would be a capacitive filter, and in this case you can certainly use a voltage doubler as shown here. In this case, obviously, there is no DC coming here because of the piezo, you have a positive current and a negative current, so this thing is balanced. You don't need an inductor, and you can use a voltage doubler. You get higher voltages, of course, or you can use a full bridge to get DC of this capacitive loading. Now, what's happening with these two type of rectifiers? Now, I'm not going into too much detail because this will take us the full day, so we'll just go on the basic relationship here. What really happens is that, say for the voltage doubler, the voltage on the output capacitor is going up until the diode starts to conduct, and then it clamps to the output. And this goes the same thing the other way. Due to the high Q of the piezoelectric element, the current within it is still sinusoidal. But the output current is coming off only when you reach the clamping voltage, so you get this waveform. This is the output current coming off the diode to the load. Now, for the current doubler, it's a sort of different situation, because here there's no clamping of a voltage. There is a voltage which is changing, but then there is a clamping actually of current, and this is the current which is the current of the two inductors of the current doubler. So it's a different waveform here. The key factors are this conduction angle, which is a function of the operating point, the characteristic of the element, etc. Now, we have found, of course, the problem that I'm trying to address is, suppose you have a rectifier. How do you calculate input to output voltage ratio? This is the problem that I'm trying to address here. And because the waveforms are weird here, the current is not sinusoidal. It's not just a simple inductor, a simple load, simple resistor. So we have found that you can use an equivalent circuit in order to represent the loading of the PT, and this equivalent circuit in general is not resistive, but it has to have also a capacitive nature. The reason for this capacitive nature is that there is a phase shift here between the current and the voltage. If you look at the first harmonic, there is a phase shift, and this phase shift you have to account by a reactive loading and not just a simple resistive loading. You just put here a simple resistive loading, this will not account for the phase shift. So we have worked out, there's some references here, and I'll spare you all the details, but just say that you can calculate. You can calculate the equivalent resistances and capacitance as a function of the load resistance for each situation, for the voltage doubler and the current doubler. Again, if you have a circuit like this, okay, and you like to find out what is the input or the output to input voltage ratio, what you basically do with this method is you first calculate this equivalent capacitor and this equivalent resistor. And then, of course, you have a simple AC network that you can easily calculate the relationship between input and output. Once you know this, you can translate back this AC using power balance between AC and DC. You can calculate it back to the DC of your actual load. Okay, so this is this method which is given in these references. Yes?
This only accounts for the first harmonic or RMS?
Well, no, it is not. It is assuming first harmonic only for this inductor current. Okay? But for these, you see, real power is coming only from the first harmonic of this current. Because if the excuse me, if the current is sinusoidal, okay, then real current, real power is generated when the voltage is the first harmonic. All the other harmonics will not generate any real power because the multiplication of a higher harmonic with this sinusoidal wave is, of course, the integral is 0, okay? So what you have to do is you have to look at this first harmonic of this voltage and take into account the phase shift between this and the current, and then I'm talking about actually and this will be the power coming off the piezo, and this is the current, the power of the coming from the piezo, and then you translate it to the load. So it's a pretty good approximation. I mean, it's not assuming that everything is the first order, which is incorrect. It is assuming that the power, the real power, is generated by, say, the first harmonic of the voltage, which is correct. Okay? So, again, this is an example here. Okay? This is an example. This an example is the equivalent AC load for voltage doubler. It's a particular case, just to demonstrate. And what it shows here is the following. If you have a transformer which is loaded by a voltage doubler, a rectifier, then depending on the actual DC load, this is the DC load, only it's normalized, okay? Depending on the DC load, you can calculate the equivalent resistor and the equivalent capacitor. And once you calculate these, you can, of course, analyze the circuit as a simple AC circuit, get the transfer function, and then from this go back and get the DC from power balance between the AC and the DC. Okay? So this is the concept here. Once you do this, obviously you can go back to the method that I've mentioned, and that is translating or transforming the parallel branch here into a series branch, and of course get this transfer function in a simple way. Let me sort of give you the bottom line of what you can do with this analysis to find out some general characterization of the different rectifiers. Okay? Again, we are going to define some normalized parameters, which are so different, sort of different from what I showed you before, for several reasons that I'll not go into it. There is the load factor, again here, it's defined a little bit different. There is the PT factor, which has to do with the parameters of the transformer, and there's again the mechanical quantity factor. Okay? So let's have a look at sort of the bottom line here. If I plot the gain output, the DC output, to the input voltage, the AC voltage, what I'm trying to do, I'm trying to compare the voltage doubler to the current doubler, the two types of rectifiers. And I'm finding something which is a little bit strange, but that's the way it is. Over most of the load resistances, the two are about the same. However, at high loading resistances, the current doubler stops to the gain of the current doubler stops to increase, while in the voltage doubler it goes out a little bit and goes to a higher values. Meaning that if you need a high voltage at the output, a high gain, which is kind of intuitively very clear, you'd like to go to a voltage doubler, okay? If you want high current, then you go to a current doubler. But this is showing it in a quantitative way, okay? To show you the numbers in it. Another interesting point that comes out from this analysis is that the efficiency for the current doubler is at low resistances, while for low resistances the efficiency for the voltage doubler is very bad at low resistances. There is an optimum at the higher resistances. This is again all normalized. So again, if you have a high output resistance, the voltage doubler is the right solution. If you have a small resistance, I mean comparably, then the current doubler is a better solution. So I'm going to jump this thing because we are going to have, this is the same thing. So this means that the current doubler is indeed very good for cases that you have low resistances, and the voltage doubler is for high resistances. Now the difference between these two curves is different transformers, because the APT, A sub PT, is actually describing the quality or the nature of the transformer. It has some parameters in it. Let me go back for a second. Here it is. APT has to do with the resonant output and the internal resistance. Okay, so the different numbers here are actually different resistance. So there is a fine line here that means that all these region you'd like to work with the current doubler, and all this region you like to work with the voltage doubler. And this is shown in this graph in a somewhat different way. This is the region that you like to work with the voltage doubler, and this is the region you like to work with the current doubler. This is again for different transformers. So this work, the bottom line here, is using the result of this analysis. You can decide for a given application, a given transformer, and a given load, which is the better way to go, whether would like to have a current doubler or a voltage doubler. This is actually giving you a way to select the best approach. Yes?
You haven't mentioned anything that I have brought up. Due to the fact that voltage and current are not in place, we have that equivalent capacitance.
Yes?
And it's in series, you can put it in series with the capacitors.
Yes? Yes?
Don't you have any effect in the resonance frequency? Is that anything that it could be affected?
Okay, you're absolutely right, and I didn't say this, but all these results are for the optimum operating point. This is already adjusted to the change in the frequency. Okay, now as it turns out, normally this capacitor is fairly large as compared to this. So there's a small change, but all the results are for the maximum operating point. So it's all adjusted for this. But you are absolutely right that
You have to choose also.
yeah, you have to choose, you have to change the frequency, and we'll talk about this frequency changes in a second. Okay? Okay, we'll talk about it in a minute. Okay, let's go on with this. Now, I'm going to demonstrate some of these issues when talking about high voltage application. Yes, please.
Sorry, I have another question. The voltage doubler seems to me be okay with less circuit expense.
That's correct. That's correct.
But do you believe the ripple of the voltage doubler at the output is larger than in the current doubler if you use it for a DC-DC power supply?
Absolutely.
Yeah, you have
Absolutely. Yeah. Absolutely. Yeah. You.
The efficiency of the transformer itself with the voltage doubler, I am not so sure if this does not suffer.
Again. You mean the piezoelectric?
Yes.
Again, this is a pretty good picture what it is.
Yeah.
As you see here, there's a slight. This is the same transformer.
Yeah.
So there is a slight change in efficiency, okay? Yeah, I didn't mention it. You're right. But it's not very large. It, of course, depends on the transformer. There are many parameters that affect it. There's a slight change. But the point is that obviously, if you are at this region and you're working at high resistances, this is the solution. If you use this current doubler, that's very bad. Okay, so you have to optimize it for the operating conditions.
Question, that is interesting point.
Yeah,
Very
yeah,
interesting.
yeah. That's what it is. Okay, let's go now to this high voltage. Now there are some applications that you like to generate high voltages, and the piezoelectric transformer is really a very good choice for that, because you can get high gain with the rosin type. You can get good insulation because of the ceramic material, and applications that have been already using these capabilities are for ionizers. I mentioned this, ozone generators, and sparkers. This is igniters for actually even for high pressure lamps. Okay, so in a simple structure, you will have, this is shown with this, you see the clamped resonant circuit here, or inductor clamped waveform, half bridge transformer. You have here a doubler, and here's the load. Okay, now this is a typical result. You see that with one single transformer, I don't remember the input voltage, it wasn't very high. You get up to, say, 6,000 volt, which is really very impressive. But obviously, the power level is low, so we are talking about fairly large resistances or load resistances. This is after rectification. Okay, we are talking about DC here. Now, but you get this curve only if you adjust the frequency. This is what we just talked about. If the frequency is kept constant, that's all what you get. Okay? So you really have to be very carefully to adjust the frequency. And here is, for example, for this particular case, what you have to do. In order to get optimum for each particular point, you do have to change a little bit the frequency. It's not a lot, but since the quality factor is high, then obviously very small changes will already ruin the whole thing. So a big issue is how to track the frequency. Obviously you cannot do it manually, and you do have to, well, if you have many students, and of course you can take one of them and adjust it, but in real life you'll have to do something. Okay, so here is an idea that has been explored and actually been used to do automatic frequency tracking. Okay, what's the problem? The problem is that we want to always be at the optimum point when there is some changes here, and you have to a little bit change the frequency. Now, as it turns out, the optimum point is basically when this branch here is in resonance. But this is the mechanical branch. You don't see, you don't have access to it. You cannot get into it. However, if you have a doubler, fortunately, part of this current is coming off here. So if you look at the diode current, here it is, you basically are sampling this current in this branch. So what you'd like to do, you'd like this current, which is sensed by this diode, to be in phase with the input voltage. Because when this is in resonance, you have here a resistive nature, and the current will be in phase with the input voltage. So you can sense this current here, look for this point, this is the phase of the current. Compare it to the phase of the input voltage, and if there is a discrepancy or there is a difference, correct for it. And here's what can be done. Okay? So we have here again a half bridge which is clamped. Here is the transformer. Now we sense this current by a comparator. We sense the input voltage by another comparator, and actually there's a clamp here, of course, there's a high voltage here, so you just sample some of it. So here, this output here gives you a square wave in phase with the input voltage, and this one gives you a square wave which is in phase with the current through here, and this is the current through the PT. You compare this phase to this phase by a phase detector, and you feed the error into a VCO. That's a phase lock loop, that's what it is, and this is the drive. So by doing this, you can track the frequency, and this is very important in situations like, for example, if you have charging capacitor. So suppose you like to use this for charging a capacitor and then discharging into, say, a spark air or gap, a spark gap or something like that, and then it starts again. And through this period, the frequency, the optimum frequency, is changing all the time. So you have to track it. And this circuit will do it automatically by measuring here where it is, measuring again the current which is reflected from here, comparing to the input, and here we have a performance of this circuit. The two curves are the output voltage, and in this case there was a change in the temperature. So the parameters of the piezo are changing, and consequently you have to correct by changing the frequency. Now if you run it at a constant frequency, that's what will happen. It'll just drop very much. While if you are correcting it automatically, well, there's some error here, but this is holding up pretty much. Yes, please.
How about the output capacitance of the PT? Is it small relatively?
Well,
The current through it, I mean.
you mean the current through this capacitance?
Yes.
Okay. It's yeah, I don't know if I can have it here. Okay. You are talking about the fact that we are sort of losing some of the current through here and not here. Okay. We did some analysis for the Rosen type, and it turns out that this is negligible small. There's a paper on that. It's referenced here, and you can see it here. It's a good point, but it's a small. Yeah, it's a small effect, but it's correct that there is a small problem, theoretical problem here. Okay, so this is the end result, and as you can see, this circuit works very well. And in situations that frequency might change, it always keeps it at the optimum. Okay, I'm going to move now to a different rectifier, and that's a resonant rectifier. And this is for the situation in which we have a generator or a damper. We talked about it at the beginning, which is a current source. And we would like to harvest, to get maximum energy out of this, electrical energy. And as I've showed you in the first part, in the introductory part, there is a problem here. The problem is that part of this current is circulating through the output capacitance, and it's getting lost. So there is that much power you can get with just loading it. Now here is in a way to overcome this problem. And the idea here is that we are not using this small generated current for the purpose of commutating the capacitor. Rather, we have an auxiliary resonant circuit that, when times come, and I'll talk about it, will cause this voltage across the capacitor to resonate with this inductor, and this will flip the voltage by itself without the need for this current to come from here. Okay? So this is sort of self-sustaining thing. Obviously, there are some losses that you have to overcome, but in general, I mean, in principle, you don't need this current, this input current coming from the piezoelectric generator to change the frequency. So here, how it works. Suppose we are, say, at the point that the current is changing polarity, then there will be some change of voltage here. So say the voltage is going down. This change of voltage is sensed by this differentiator, and it is flipping this comparator, and it is toggling these switches. So suppose the voltage was here plus, it will close this switch. When this switch is closed, then there is a resonant path like this, and this will cause a resonant current to generate. It will increase the current, and then eventually, of course, start building up a voltage which is positive here and negative here, until the current will drop to zero, and that's it. Because of the diode, will not reverse. So here we see it here. As soon as the voltage started to change, this whole part was caused by, this is the detector, and this is the resonant part, and this whole part has was commutated by the resonant part. Unfortunately, due to losses, some energy is lost, so you're not coming back to exactly the same voltage. So this part here is coming from, again, the input. This is energy that you still need, or current you still need to change the voltage to the output voltage, and then, of course, you get the output current. Okay? So this circuit is sort of optimizing this, and is enabling one to get at least 50 to 100% more power from this tiny generator. We're talking about generators that at best will give you tens of a milliwatt. Okay, so every milliwatt counts here. So you have to be very carefully. This was tested on this experimental circuit, which you see is self-sustained. We have a comparator here which is powered by these two voltages from this coming off the transducer itself, and the derivative is done by just a passive network here. So when the voltage is changing, this will cause this comparator to change states. It'll turn on or off one of these FETs. It'll turn this resonant circuit, and by this you will commutate this thing. This was tested by a circuit that was actually vibrated by another piezo, so we got basically a vibrating system. I did mention now, or I've said at the beginning, that we have two appendices attached. One of them, B, is describing this in full, and you have all the waveforms and results, etc. And I just was afraid that I will not be able to go over it in detail. So whoever is interested, in the handout you have, and also in the CD, you have this. And this was also published in here. And you can get our papers. Published papers, off our website, because most of them are in PDF. You can download them from our site. Okay. Now I'd like to dedicate the time that is left to an issue which is a hot issue, and it's still not completely resolved, but as you'll see, there are some results already, and that is instabilities that can happen when you are feeding a fluorescent lamp by a piezoelectric transformer. Now, if you look at the characteristics of a lamp, cold cathode fluorescent lamp, typically this is type of a curve you get. This is RMS lamp current, and this is RMS lamp voltage. This is for these tiny lamps, say 2 millimeters diameter, that are used, say, for here, backlight for this, say, laptop or LCD monitors. Now, these are, however, RMS voltages and currents, steady state. In order to get to the operating point, you first of all have to overcome this maximum, which is actually the ignition voltage. So your piezoelectric element, if you are using one, has to generate, say in this case, 850 volts at least 1 milliamp in order to sort of cross this peak, this mountain, and get to the operating point. So this is one issue that has to be carefully examined, because sometimes you will find a piezo which can very nicely operate here, but it cannot pass this point, and it will not start. You need either an outside igniter, you have to increase the voltage to do something else. It will not ignite the voltage, okay? So this is one issue. Another issue, okay, this is what I've just said, that you need, of course, ignition, and of course, you need the piezo to deliver the right power, okay? In this case, say about 4 milliamps and 600 volts. Now, another issue, which I'd like to address here, is the problem of instabilities that you can run. You can, in some operating condition, what you observe is when you hook up a piezoelectric transformer to a cold cathode fluorescent lamp, you start having oscillation. It's not stable. It is oscillating. This will be the current, and this will be the voltage. The reason that you see it a little bit, and the reason you don't see it in the voltage is because this curve here is for the voltage is flat, and so therefore you don't see it, much change in the voltage. Excuse me, here. Okay, you don't, for a large excursion of current, the voltage change is only small. Okay, so this is the problem that you have. And what I'll try to do now is to explain this phenomena and to show why this is happening and how can you study it, although we don't have a good cure for it, but at least we understand what's going on, okay? Okay, now let's have a look at the problem of stability. The simple explanation of the need for a ballast for a fluorescent lamp is this curve. This is a very simplistic explanation. What does this say? It says the following. If this is sort of a linearized characteristic of the lamp, okay, what we've seen before, this is just replacing by a straight line. Then you can operate it by something that looks more like a current source. A pure current source will be a straight line. A pure voltage source will be like a horizontal line. This looks more like a current source. This looks more like a voltage source. Now, the explanation why you need something that will look like a current source is the following. If there is a, let's see if I have it here. I don't have it here. If this is the operating point, and there is some change in the current, so you move, say, to this point. If the ballast is a current source, what happens is that there is a big difference now between the voltage source and the voltage of the lamp. The voltage of the lamp drops down. Consequently, the current will increase. And as the current will increase, the whole thing will collapse. On the other hand, if this is a current source, then the voltage across it becomes smaller. And the smaller current will decrease the current of the lamp. So this is a very, this is a classical explanation, but it's wrong. The reason is that we are dealing here not with DC, pure resistances. We are dealing here with a dynamic system which has a dynamic behavior. It has poles and zeros, and it has resonant points, and this doesn't show any of this. Okay? So we need something more, let's say, more relevant to the problem that we have. First, we introduce here the fact that you see this line, this operating line, is for slow changes. As I've said, this is a RMS curve. This is RMS current of the lamp. This is RMS voltage of the lamp. You move from here to here as you change the power. But for fast changes, the lamp does not move on this line. It moves here, because for fast changes, the lamp looks resistive and not with a negative impedance, like here. It looks resistive. So if you work at one operating point for fast changes, this is what you have. And then when you move to another operating point, this is the resistance that you see. If you change the power, you'll move across this line slowly. But then for fast changes, you're here. So you have a mixture of fast behavior and small behavior, and they are not the same. Okay? Now you can model this thing with an equivalent circuit of the lamp, which shows the following thing. This is the lamp. Shows it as a current source. But this is not a constant current. It is dependent, this current, dependent of course on the voltage, because it's a current, dependent current source, or like a conductance, but it is dependent on the equivalent resistance, which in turn is a function of the RMS current. So for any given operating point, this is something different. Now, the value of this thing you can find by looking at the current of the lamp, squaring it here, this is squaring it, filtering it out, this is actually doing RMS. If you square and filter, it's actually doing the power, average power. And when you take this square root here, this is the RMS. So this is the RMS of the current. And if you fit this R equivalent to the RMS current, then you can fit this model to any given lamp. Okay? As it turns out, for small changes, the impedance, we call it the incremental impedance. What is the incremental impedance? This is a small change in voltage divided by the small change in current. Has this nature. This has been shown by people from the physical domain, and this comes out from this model, as a matter of fact. What this shows is a very interesting thing. If you look at this function, this is the impedance. At very high frequencies, when this goes to infinity and this goes to infinity, okay, this is negligible, and then it divides out, this divides out, and you end up with R equivalent. At very low frequencies, when this is about 0, this is about 0, you have minus 1 times Rs, this is the negative resistance. So this shows that for small resistances, small frequencies, you have indeed this negative resistance. But as the frequency goes up, it becomes positive resistance. So this is now this behavior. This is, well, it's the admittance, 1 over the impedance. Small frequencies, okay, you have this value of the resistance, but 180-degree phase, which means it's a negative resistance. As you go up in the frequencies, you end up with a positive resistance, zero phase, and this value of a resistance. This is admittance here, but this is 1 over the resistance. So this actually explains what is the behavior of the lamp. So here we see this effect. If you change the current, do a modulation on it, and if the frequency is small, you see that the voltage responds in the opposite way. For a decrease in current, the voltage goes up. For an increase in current, the voltage goes down. This is because of the negative resistance of the lamp, the incremental resistance. However, if you do the same thing at high frequencies, you see that this incremental resistance is positive because a reduction in the current goes along with reduction in the voltage. So this really shows this phenomenon. Well, let me skip this thing. Okay, so now we come to the problem of stability. Okay, we have the ballast, we have the lamp. What are the conditions of stability or instability? One way to look at it is try to change it into a feedback network. Try to change it such that this thing will look like a feedback network. The reason we would like to do it, because for feedback we have this criteria of loop gain, phase margin, and we can handle it. Okay? Now how can you make this to look as a feedback network? Look at this. The ballast is a voltage source and has an internal impedance, looking here. And this is your load. This is the lamp. So you have a voltage imposed on this ballast, generating a current, and this current is flowing through the lamp. Okay? Now, what is the voltage on the ballast? It's the difference between the voltage here and the voltage here. This is the voltage across this. What is the voltage of the lamp? It is the current times the impedance. So you can show this in this feedback scheme, which is very familiar and can be handled. What do we see here? This is the excitation. This is this. Minus the voltage on the lamp. This is here. The difference is the voltage on the balance, or the ballast. This is the difference. Divided by the ballast impedance, the difference divided by the ballast impedance is the current. Here is the current coming in. And this current, when flowing through the impedance of the lamp here, is generating a voltage, which is the voltage of the lamp. So as you can see, we can translate this situation of a source feeding a load into a scheme that looks like a feedback circuit. And we know that for this feedback to be stable, we have to look at the loop gain. This is the product of this times this, the product here. And if we look at the loop gain, that is dividing the impedance of the lamp by the impedance of the ballast, we have the key for analyzing this circuit and knowing whether it will be stable or not. Okay? So the key factors are the ratio between the impedance of the lamp and the impedance of the ballast, of course, over the frequency range, and in particular when the gain is 1, and this is when we are looking for the phase margin, because the phase margin is the phase of this thing when the loop gain is 1. Okay. Now the question is, what is the impedance we are talking about? What is the impedance? it would look as if we have to talk about this impedance. This is like the impedance of the ballast, and this would be the impedance of the lamp. But you see, this is not the true story, because we have here a situation that this system is driven by a carrier. And I can, if you look at this system, you realize that if the carrier frequency is very high, this system will be always stable. Because if the carrier frequency is high, this is a short, this is a very high impedance, this is a current source, it will be always stable. On the other hand, if the carrier frequency will be close to the resonant frequency, this impedance is very low, at resonant it's 0, this is a voltage source, this will be unstable. So what we have to look is not at this impedance, we have to look at the incremental impedance. That is, what is the impedance of this branch when you have a carrier and you just change the amplitude, say, of the voltage, what will be the change of the current? So this is the concept of incremental impedance. This is what we talked about when we talked about the lamp, and now it turns out we have to talk about the incremental impedance of the driving network, because this is the key parameters, not just the simple impedance, but the incremental impedance. Okay, now how does an incremental impedance look like? That is, we're asking the following question. There is a carrier, there is a modulation on it, say of a current, and of course you will see a modulation on the voltage. And I am interested in this ratio between this voltage and this current. This is the incremental impedance of this network. Okay. Now how does it look? Let's just understand it intuitively without going into too much mathematics. So suppose you have this network. Okay? You feed it by a modulated signal. And you change the frequency of modulation. You change it. What will happen here? You see, this is the admittance of this network. Of course, it's a resonant network. At the resonant, it has the lowest admittance. This is actually this resistance. Okay? Suppose this is the carrier frequency here. Okay? It is AM modulation. AM modulation has two sidebands. Okay? So you are feeding this network with this signal, composed actually of 3 components. Now when you change the frequency of modulation, this moves. Okay? It will move and eventually it will hit this point. And at this point you will have a peak in the current, because the sideband is exactly at the resonant. The frequency that you'll have this peak is not this frequency. I'm talking about the frequency of modulation here. It'll be the difference between this frequency and this frequency. Okay? So incremental impedances are not directly related to this resonant network. It's a more complex situation. It's the difference between the carrier frequency and the resonant of this network. And this is where the peak or the peaks you will find for this incremental resistance. Now, you can do this if you want analytically, I mean analyzing this circuit, but this will be very complex, very, very complex, because the trigonometric function that you'll have here will be horrendous. A way to handle it is to use what we call envelope simulation. Now, what is envelope simulation? This is a technique in which, rather than looking, let's say here, about the full waveform, you just look at this envelope. And as it turns out, you can do it by simply converting this circuit to a somewhat, actually two parts, with a technique that we call envelope simulation. And by doing this, you get rid of this carrier and you just are dealing with this envelope. This is very effective because simulation, of course, is very fast. You don't have to deal with all these high frequency components, and then you can look at the picture that you want to see, and this is indeed giving you information about these incremental currents and incremental impedances, which are the ratio, which are in the envelope, not in the carrier. Okay? So this technique of envelope simulation is described in Appendix A. I'm sorry, we just don't have time to go over it. And whoever is interested can look at this appendix and also in these references. This is explained how to do envelope simulation. And just as a way of an example, I'm going to show you an analysis of a specific case. We have an experimental circuit. This is the circuit for which we had measured, this thing. Okay? This is a measured phenomenon. And now we're going to analyze it by using the concept that I was talking about: incremental impedances, feedback network, etc. Now, the first thing to do is, of course, to describe the equivalent circuit here, which I'm not showing. And that is to model the piezoelectric transformer by the equivalent circuit. And then to translate it into the envelope simulation. It looks frightening, but it's really not that complex. What basically it is, we have two circuits here, which turns out are the real part and imaginary part of phasor presentation of the waveform. Okay? You can see here, this is the resonant inductor, this is the resonant capacitor, this is the output transformer, this is the load. We duplicate it into what we call the real part and imaginary part. And we excite it with a certain way of excitation, of driving signals. As it turns out, when you duplicate it, you have also to add some dependent sources, and the dependence is for the two parts. That is, there is a dependent, in this case, current source, which is a function of the current here, and there is a dependent current source, which is a function of the current here. Okay? So this is part of these techniques of envelope simulation. You run it, there's no high frequency components here, only the envelope is running here, and then you take the square wave, you take the root of the, let's say it's here, it says here, where it is, here. You take this square root of the voltages, square voltage here and here, okay, like the absolute value. And here is something, a typical result that you get. What do we see here? This is the phase and magnitude of the incremental admittance of a piezoelectric transformer. Okay? This is frequency here from 100 hertz to 10 kilohertz. Again, this is not high frequencies because all the phenomena we see in the envelope are low frequencies. Let's concentrate on this one, the brown one. Okay? This is a carrier frequency of 65 kilohertz. You see here the incremental impedance. has a peak around 1 kilohertz. Why? Because the resonant of the PT is about 66, the carrier frequency is 65, so the modulation for the peak value is about 1 kilohertz. These are rounded numbers. Now, if the carrier frequency is different, like 60, you get, of course, the peak somewhere else. So what you see here, that in order to understand what is going on, you have to specify at what carrier frequency you work. It will behave different at different carrier frequencies. Okay? Now, once we have this incremental impedance, and now we have the lamp, and from the model of the lamp we can get the incremental impedance of the lamp. This is the incremental impedance of the lamp. Once we have these two, we can take the ratio, or which is the loop gain, and see what's really happening. And here are some results. You see that for a particular case, for a carrier frequency of 75 kilohertz, the loop gain, which is the product of this impedance, which is obtained by this envelope simulation, and the ballast, which is the piezoelectric transformer, also obtained by simulation, gives you this. This is for positive and negative frequencies, okay? This Nyquist plot. And as we know, since this plot is not encircling the -1, then this is a stable system. Now, if you change the carrier frequency, it turns out that for this particular case, the incremental impedances are changing such that this particular one is really encircling the -1 point. So this is an unstable system. So what we see here, that the crucial parameters are the incremental impedances of the elements that you have to look at by sort of envelope simulation, or by some other means, not the impedance of the total impedance of, say, of the piezoelectric transformer. It's not important. What is important is the incremental impedance for small changes, because you are running it at a given carrier. You are sort of stabilizing everything around a given point, and the question is then, how will this system behave around this point? And it will behave differently for one carrier than another carrier, as I showed you. So by this, we can very nicely analyze the system, and indeed, you see that in simulation, for this particular unstable case, when you put the right case state, the carrier frequency, etc., and run a simulation on the total system, you indeed get instabilities very similar to what we are getting, of course, in the experimental case. So, as I've said, I think we are approaching a good understanding of this phenomena, and what is an open question now is, what are the means that you can do in order to stabilize the system? And if I look at it in a very, very simple case or situation, what really is happening here is that when the lamp is looking back at various carrier frequencies, the incremental impedance is really changing very much. Because, for example, if you are at around the resonant frequency, this is a short here, so you see more a voltage source than a current source. And no wonder that there's a problem here. So the question is, how can we maybe work at certain carrier frequencies that will be away a little bit from the resonant frequency and some other means? This is really an open question, something for, I guess, next PESC conferences. So I think this is about the time for me to close. We just about finished the time, 5:25. So what I try to do is give you in a short time an overview of the major piezoelectric elements that are now practical and useful and really are used in various applications. My emphasis, of course, was on the power electronics part because people here are not physicists or material engineers, and what we are interested in is, of course, how to drive the elements, how to harvest, how to rectify, etc. Now, it's clear that the prices are dropping down, and obviously the element will become more and more economical in many applications, and we hope that this information will be useful when designing system, analyzing them, etc. So I thank you very much for your attention, and I'd like just to acknowledge the Israel Science Foundation for supporting part of our work, and if there are any questions, I'll be more